What secrets lie hidden in the cold darkness of the lunar poles? Extreme environments conceal untapped resources and unexplained mysteries. Pieces of a profound puzzle locked beneath the dust and ice, soon to be unlocked. Now, NASA's VIPER prepares to expose the truths and tackle the challenges that the moon's pole hides. The time has come to peel back the layers of lunar mystery and reveal what's really there. What's up, spacers? This is your specialist, the Space Technician. And today, we're finding out the truth about NASA's VIPER mission to the moon's southern pole. Let's go. Remember, strapping in is optional, but recommended. VIPER stands for Volatiles Investigating Polar Exploration Rover. This name conveys its mission to explore the lunar poles and study volatiles, materials like water ice that are relatively easy to vaporize when heated. VIPER is solar-powered, with high-efficiency panels powering a non-rechargeable battery designed to withstand the extreme temperature changes on the moon. Specifically, it will map the distribution, concentrations, and physical state of water ice and other volatiles across the frigid lunar South Pole region. Using its neutron spectrometer, VIPER can detect hydrogen buried under the regolith soil, that is, fragmental and unconsolidated rock material, up to 3 feet or 0.91 meters deep, with higher hydrogen levels indicating the likely presence of H2O molecular compounds. It will sample various soil temperatures and light conditions to reveal more about the depths and environments where this water ice resides. VIPER's drill, called Trident, will also directly sample below the surface using its 1-meter-long auger bit made of hardened steel. It both hammers and spins to dig down through compact soil and icy layers. The near-infrared volatile spectrometer system then assesses retrieved samples, differentiating between water, hydroxyl compounds, and volatiles like methane, which could be used as fuel. By measuring the accessibility and abundance of water ice, VIPER will create detailed resource maps showing the best locations to eventually harvest these materials. These could then provide drinking water, breathable oxygen created via electrolysis, and rocket propellant for future astronauts exploring under NASA's Artemis program in the late 2020s and beyond. So while focused on science, the rover also serves as a prospector, enabling sustainable, long-term human lunar access. NASA engineers equipped VIPER with rugged, specialized wheels and suspension to traverse the moon's uneven craters and sandy dunes. Its wheels are arranged in a unique curb climbing configuration, able to lift and lower each wheel module independently, using footpad-like actuators to get purchase on sinkable soils. Built out of tough AL6061 aluminum, these wheels feature chevron titanium treads for maximum traction. The chevrons flex to maintain contact over rocks, and cleats on the wheel's edges provide braking and stability. Each wheel also has its own individual steering motor, enabling VIPER to drive diagonally or even spin in place as needed. Weighing in at a respectable 845 pounds or 383 kilograms on Earth, the rover chassis itself is roughly the size of a golf cart at 8 feet long by 5 feet wide, or 2.4 meters long and 1.5 meters wide. However, VIPER stands nearly 8 feet or 2.4 meters tall, thanks to the solar arrays angled upward from its dual-deck body, optimizing their sunlight exposure. Riding on flexible suspension shock absorbers, called rocker bogies, VIPER can handle inclines up to 15 degrees and even briefly reach 30 degrees when needed. This lets our moon prospector confidently roll in and out of craters in pursuit of hidden ice deposits. So, while smaller than terrestrial rovers like Curiosity on Mars, VIPER makes up for it with agility and innovative design focused on mobility plus resilience in punishing polar environments. Key to finding buried ice is the Neutron Spectrometer System, or NSS. This detects subsurface hydrogen by measuring neutrons naturally emitted from the soil. When neutrons hit hydrogen atoms, they lose energy, allowing NSS to infer water deposits up to 3 feet or 0.91 meters down by mapping this hydrogen signal. Once NSS indicates subsurface ice in an area, VIPER deploys its drill, called Trident, to directly sample below the lunar surface. Using its hardened steel auger bit, Trident can hammer and spin to penetrate up to 1 meter deep in compact regolith soil. As it drills, it monitors temperature gradients in the borehole. Retrieved samples travel up the drill flutes to a chamber where the near-infrared volatile spectrometer, NIRVSS, shines infrared light to detect and characterize different compounds. It can differentiate between water, hydroxyl, and other volatiles, like methane, which absorbs particular wavelengths. Meanwhile, the mass spectrometer observes lunar operations, or M-SOLO, verifies which gases come directly from the lunar soil versus the drill itself, letting scientists focus on native lunar volatiles. VIPER's cameras support 3D terrain modeling for planning drives between science targets, while monitoring wheel traction and bearing loads to avoid getting stuck. The engineering telemetry will help design future polar rovers. To enable non-stop operations, VIPER has a specialized battery and power system to survive frigid -300°F or -184°C nights. Its smart thermal control activates electric heaters to keep systems functioning in the shadows when the sun dips for 14 days at a time. The moon's south pole is one of the most extreme environments in the solar system. Frigid temperatures swinging from -280°F or -173°C to 260°F or 127°C as sunlight sweeps across the landscape. VIPER must withstand these dramatic thermal shifts without freezing or overheating. Its warm electronics box and heated batteries allow continuous operation through the long, icy nights. The rover also has to balance power between darkness and constant sunlight. Solar arrays recharge VIPER's battery to keep exploring the shadowed craters believed to harbor ice deposits. But it must retreat back out to sunlit spots to recharge when reserves run low. So VIPER plays a delicate game of balancing power and temperature to maximize science time. Dust possesses another threat. Lunar regolith is extremely abrasive and sticky. It coats surfaces, clogs mechanisms, and erodes materials. VIPER utilizes dust-resistant seals, special space grease, and operation protocols to mitigate effects. Still, accrued dust may eventually threaten operations, as it did for Apollo missions. The rover's software leverages advanced obstacle detection and path planning algorithms to navigate hazardous rocky terrain. Machine vision identifies slopes and boulders to avoid as VIPER rolls between science sites. It requires no direct human control, thanks to autonomous driving assisted by Earth-based navigators. And communicating from the stark lunar far side lacking orbital relay satellites poses challenges. VIPER's positioning considers line of sight for direct Earth communication, planning driving routes to keep small surface landmarks from blocking the signal. To test performance in lunar conditions, early versions of VIPER's 3 main instruments will fly to the moon's surface on precursor lander missions. NASA's Commercial Lunar Payload Services (CLPS) program allows companies to bid to deliver instruments as a rehearsal. The Near-Infrared Volatile Spectrometer, Neutron Spectrometer, and Mass Spectrometer will practice observations from the harsh, airless regolith environment before VIPER. Engineers will evaluate their endurance of temperature swings down to -300°F or -184°C, vacuum exposure, radiation, micrometeoroid bombardment, and lunar dust. Any failures will drive design tweaks. This strategy echoes NASA's "test like you fly" ethos, spotting issues early to improve later mission outcomes. After this trial by fire provides confidence in the instruments, VIPER carries the next generation versions across the frigid lunar plains. NASA's Mission Operations Center will directly control VIPER's activities from Earth. Unlike fully automated Mars rovers, Given the Moon's proximity with only 1.3 light-second signal delay, tight command feedback loops enable teleoperation. Operators practice for over a year using VR simulations to become adept at low-latency lunar driving. VIPER's waypoint navigation has Earth-based drivers analyzing navcam imagery to chart safe courses through hazardous terrain at walking pace. If needed, they command VIPER's wheels to lift independently for purchase on slippery slopes. Specialist teams coordinate closely on driving, drilling operations, and instrument observations. For example, before deploying the drill at a promising ice site, thermal experts verify temperatures won't damage mechanisms, while hammering regolith force sensors safeguard against bit seizures or snapping drill strings. Throughout the long lunar days, VIPER stays in near 24/7 contact with mission control, unless line-of-sight landmarks block antenna signals. Uplinked commands steer driving, drilling, science observations and system checks, while downlinked data monitors subsystem health and progress. This intensive direction leverages the benefits of interactivity, responsiveness, and human judgment, maximizing mission returns within engineering constraints. VIPER also employs automation algorithms from self-driving cars, like the open-source Robot Operating System, ROS2, fused with oversight. In many ways, VIPER pioneers a new hybrid paradigm, balancing autonomy with instant human control never before possible on Mars and beyond. Its successes will shape future planetary rover architectures. VIPER has two high-level science objectives for its roughly 100-day lunar prospecting campaign. First, map the distribution, concentrations, and physical state of water ice trapped in frigid polar craters that never see sunlight. Are deposits shallow chunks of pure ice, or scattered molecules chemically bound to soil grains? This helps gauge accessibility. Second, determine the origins and source of this lunar water over billions of years. Did it arise from solar winds implantation, comet impacts, or volcanic outgassing? Are reserves still accumulating? The source shapes prospects for mining extensiveness. Achieving these goals involves sampling various soil temperature gradients and light conditions. VIPER's instruments measure subsurface ice abundance, while its drill retrieves samples from the depths down to 1 meter for detailed on-site analysis. All this aims to ground truth orbital measurements, suggesting billions of tons of lunar ice locked in polar cold traps. VIPER gathers hard data on the practicality of one day living off the land via in situ resource utilization. Its resource mapping literally scopes out cosmic oases, where future astronauts could mine water for drinking, growing food, producing fuel, or breathable oxygen. So, VIPER plays explorer, miner, and trailblazer all in one, scoping lucrative lunar acreage for settlers not far behind. In summary, VIPER will leverage tons of cutting-edge robotics and science with the lofty goals of prospecting for lunar resources, testing technologies, and expanding our knowledge to kickstart an exciting new era in lunar exploration, blazing a trail for sustainable exploration and busting myths about the moon's bleakness. Let me know your favorite parts of this mission in the comments section below. And, as always, thank you for watching. Be sure to smash notifications by ringing the bell to see more epic space tech content as soon as I post it. This is your space technician, signing off for now. And I'll see all you space cowboys in the next one.